Today we'll be working on finding the nth apparent term of a sequence. In these problems, what will happen is they are actually going to give us the sequence of numbers, and we are supposed to come up with the formula to find the nth term. One of the things that you're going to need to keep in mind is there are some special sets of numbers that are pretty common in these problems. The first set is the set of perfect square numbers, 1, 4, 9, 16. So anytime you see those, or some variation of those, because sometimes you might see, like, instead of 1, 4, 9, 16, you'll see like 0, 3, 8, 15, where they're one less than a perfect square, or maybe one more than a perfect square. Another very common set of numbers to see is the numbers 1, 2, 6, 24, 120. Sometimes you'll actually see like 1, 1, 2, 6, and those are your factorial numbers. So this would be 1 factorial, 2 is 2 factorial, 6 is 3 factorial, and don't forget that the beginning 1 is actually 0 factorial. Let's say we're given a set of numbers 1, 3, 5, 7, and we're trying to find the formula for a sub n, so that if I put in n is 8, I could tell you the 8th term of this sequence. One of the things I like to do is kind of arrange these in a table. And what I'll do is I will have a column that has the term, like first term, second term, and so on, and then the value of that. So I would arrange my table like that, and what we're looking for is what happens when you have n, what value will I get, because that's going to give me my formula for a sub n. One of the things that I can look for is something called a common difference. And if you'll notice, I've got the term values increasing by 1, and I always want to have those increasing by 1, and my values are increasing by 2. Well, what happens when I can find the values and they are increasing by a constant, that means my formula is linear, because really what you're finding is the slope. So I know my formula is going to be a 2n because my slope is 2. And then I just have to adjust by, is there a number I need to add or subtract? Well, let's just pick a term, let's say the third term, and substitute in 3 down here for n. Well, 2 times 3 is 6, but the third term is supposed to give me 5. So that means I need to subtract 1. So I think my formula should be 2n minus 1. So let's go ahead and put down a sub n is 2n minus 1, and then we'll check that with one of our other terms. So I'm going to substitute in, let's say, 4. And I'm just randomly picking a number out of our table. And let's see if it gives me 7. So 2 times 4 minus 1 would be 7. So I do know now my formula for my nth apparent term, my a sub n, is 2n minus 1. Let's look at another problem. Say we have the numbers 7, 13, 19, and 25. So let's make our table, term and value. Now the table is optional, but I find that it helps me to organize my numbers. So we know the first 4 terms and their values. First thing I check for, again, notice my terms are increasing by 1. And I can tell quickly that everything is increasing by 6. So this has to be a 6n formula. Let's pick a number. So this time I'll use the second term. So 6 times 2 is 12, but I need to have 13, so I need to add 1. So my a sub n formula should be 6n plus 1. And we're going to check that for another number out of my sequence. So let's try 4. So 6 times 4 plus 1 would give me 25, and my fourth term is 25. So I do have the correct formula. It should be 6n plus 1. Next, let's look at this set of numbers. You've got 2, 5, 10, 17. So if I make my table, it's apparent that if I do my common difference, we do not have a common increase this time. From 2 to 5 goes up by 3, but 5 to 10 goes up by 5, and 10 to 17 goes up by 7. But look and do a common difference again. From 3 to 5 increases by 2. This increases by 2. So since it takes 2 common differences to get out to the same number, that tells me that this is going to be a quadratic. So it's going to have an x squared or an n squared in it. Now, I'm going to keep these very nice for you because they can get very complicated to figure out the formulas. So let's try n squared. So if I take 3 as my kind of checkpoint, 3 squared is 9, but I'm supposed to get 10. So I want to add 1. So it looks like my formula should be n squared plus 1. Well, let's go ahead and check that one more time with a different number out of my chart. So let's go back and try 2. So if I put in 2, we think our formula is n squared plus 1. 2 squared plus 1 is 5, and my second term is 5. Now let's consider a problem that involves fractions. And if you'll notice that the fractions have not been simplified. I mentioned on a couple videos before that we would not want to simplify our fractions because a lot of times it makes it very difficult to find your formulas. So what I do with fractions, a lot of times there are different formulas for the numerator and the denominator. So I'm still going to make my table, but I'm going to divide it up into numerator and denominator and kind of make it a twofold table. One to help me find the formula for the numerator and one for the denominator. Let's focus on the numerator first. If we look at our numbers, from 1 to 4 increases by 3. 4 to 7 increases by 3. So I can tell that this is going to end up being a linear problem, and my slope is 3. So then I know that this goes 3n. And then let's see what happens when I pick a value to try. So let's try 4. And again, I'm just randomly picking a number. So if I put in 4, 3 times 4 would be 12. But the answer for 4 is supposed to be 10. So I need to subtract 2. So the numerator should be 3n minus 2. Let's go ahead and check that with another set of numbers. Let's try 2 and 4. So if I do 3 times 2, that's going to give me 6, and 6 minus 2 is 4. Now, for the denominator, look at your numbers. 1, 2, 6, 24, 120. Those are my factorial numbers. There's 1 factorial, 2 factorial, 3 factorial, and so on. So it looks like we have, for our denominators, n factorial. So my formula for a sub n is going to be 3n minus 2 over n factorial. We're going to wrap up with some problems that are similar to what we were doing, but this time what we're going to do is we're going to rewrite these problems in sigma notation. Now remember that what we're doing is we're now taking a series of numbers where we're going to be adding them together instead of just having a sequence and trying to write that using my sigma notation. So the same thing still applies, that I want to look for my pattern. So if I look, I can make my table. I didn't fill in the entire set of numbers because I have enough here to tell what's happening. From 4 to 9 increases by 5. So I can tell that my common difference is going to be 5. So my formula for a sub n is going to be 5n. Let's pick a value. So let's substitute in 3. 3 times 5 would be 15. I need to get 14, so I need to subtract 1. So my formula becomes 5n minus 1. Now I can write that in sigma notation. I know that this is 5n minus 1, and I just need to get my upper and lower limits. So if you'll look, we started with n equals 1. That's the first term. And if you count over, you'll find that you have a total of 7 terms. So I want to go from n equals 1 to 7 and add up 5n minus 1. Continue with the same process. What if I wanted to write this in sigma notation? Well, this one is a little easier because they've not simplified my numbers. So all I want to do is look through, and the first thing I notice is that all these numerators stay 5. So I'm going to start with 5 for my numerator. And I also notice that all the denominators have a 1 plus. And then notice what changes. So we go 1 squared, 2 squared, 3 squared, and so on. So I'm adding whatever term we're on, so that would be n squared. And then my limit would go from n equals 1 up to, I went out to 6 squared at the end, so it'd be from n equals 1 to 6. All right, for our last example, we are trying to write this in sigma notation. And again, what I notice is that all of these start with a numerator of 1. And in the denominator, notice you really have two different sets of numbers here. So the first number in each of these products for the denominator has a pattern, and then the second number has a different pattern. So we're looking for the different patterns for each of those sets of numbers. So let's focus on the first numbers. They go 4, 5, 6, 7. So we're counting by 1. So we know that this is going to have a slope of 1. So it's just going to be n. For the first term, I start with 4. And if my formula starts n to get to 4, I would need to add 3. So to get the first term, I do n plus 3, and that makes sense. When I do the second term, n plus 3 would be 5. The third term, 3 plus 3 would be 6. Now what about the second number in each of these? So let's look at those. We have 2, 4, 6, 8, and I notice that those are increasing by 2's. So that means it's got to be a 2n problem. So when I put in n equals 1, 2 times 1 would be 2. When I put in n equals 2, 2 times 2 would be 4. The first term had 2 for the second number. The second term had 4. The third term has 6. So it looks like it's just going to be 2n. Now we do need to add our limits on here. So we started with the first term, second term. So this does start counting n equals 1. Then we also need to count out how many terms do we have. Well, if you'll notice, there's a total of 7 terms. So I'm going to go from n equals 1 to 7. And now let's go ahead and double check one of these. So let's look at the 6th term and make sure that we do end up getting 1 over 9 times 12. So if I put in 6, I'd get 1 over 6 plus 3 would be 9 times 2 times 6 would be 12. And that is my 6th term.